Bioremediation is the process of using microbial metabolic potential to decontaminate polluted environments. It can be affected by pH, temperature, metals, toxic compounds, water content, nutrient availability, bioavailability of pollutants, and co-metabolism. The earliest form of bioremediation was in 600 BC by the Romans. They built intricate networks of sewers with collection vats and lagoons where microbes would naturally degrade the waste. Today's method has added aeration to the process to aid the microbial digestion. The big push from bioremediation research came after its successful use in the Alaskan oil spill of 1989 and the Megaborg spill in 1990. However, during early stages of research, developed methods typically remove contaminants from one medium just to place it in another.
Deinococcus radiodurans is genetically modified to be able to consume and digest toluene and ionic mercury from radioactive nuclear wastes. Geobacter suffreducens turns dissolved uranium into a non-soluble collectible form. Dihalococcoids ethogenes is currently used in 10 states to clean up chlorinated solvents which have been linked to cancer. It is also naturally found in soil and water and able to digest solvents much faster than the traditional cleanup. An enzyme from a bacterium, Thermus bracchianus, is found in Yellowstone National Park and breaks down hydrogen peroxide 80,000 times faster than current chemicals in use. Alkalogenes eutrophis naturally degrades 2,4-D, the third most widely used herbicide in the United States. In situ bioremediation methods treat the contaminated material on site. The methods include bioventing, biostimulation, air sparging, natural attenuation, land farming, phytoremediation, and bioaugmentation. The target contaminants are usually fuel, non-halogenated, volatile organic compounds, semi-volatile organic compounds, pesticides, or herbicides. Most of the methods are not very effective with halogenated contaminants if the compound is tightly bound to soil particles or if there are high concentrations of inorganic salts, heavy metals, or organic compounds. Bioventing involves stimulating aerobic biodegradation of soil contamination by delivering oxygen to the subsurface where indigenous organisms capable of degrading the contaminant are already present. The cost is typically $15 per cubic yard of soil and uses simple, inexpensive, low-maintenance equipment. However, this method is not effective if the water table is too high or moisture content is too low. Biostimulation is when biodegradation is stimulated by the addition of water-based solutions carrying nutrients, electron acceptors, or other amendments to indigenous organisms capable of degrading the contaminant. The cost for this method varies tremendously from site to site. Air sparging involves delivering oxygen below the water table to stimulate aerobic biodegradation of contaminated groundwater using the indigenous microbes. It has been successful in restoring polluted groundwater aquifers. The cost can be less than $1 per 1,000 liters. It is definitely the cheapest bioremediation method. Natural attenuation focuses on the verification and monitoring of natural remediation processes while the environmental contaminants are left undisturbed. This method can be used with halogenated organics, but it requires longer treatment times. It can also be used in situations where the contaminant is strictly bound to the soil. The costs increase the more prolonged the monitoring. This process is often criticized by the public because no affirmative action is shown. It can also be dangerous if monitoring is not consistent. The contaminant can also migrate or degrade into another toxic form. Land farming is when contaminated material is excavated to the soil surface, which is then tilled in order to mix and aerate it. Biotic and abiotic reactions degrade, transform, and immobilize the contaminants. It is simple and inexpensive, but requires a lot of space. Sometimes it is not appropriate because the contaminants can be volatilized this way instead of degraded. Phytoremediation is where plants facilitate the bioremediation uptake by uptaking and incorporating contaminants into plant biomass, immobilization or photostabilization of contaminants in the subsurface, releasing enzymes into the rheosphere to act on contaminants, or stimulation of microbial mediated degradation in the rheosphere. This method is a relatively new concept that has yet to be proven in the marketplace. However, the potential is of great interest. They could be used to treat contaminants such as heavy toxic metals, radionuclides, organic contaminants such as chlorinated solvents, BTEX compounds, non-aromatic petroleum hydrocarbons, nitrotoluene emission wastes, and excess nutrients. Bioaugmentation is where microbial inoculates may be added to enhance bioremediation rates when degradative microbes do not exist or where the process is too slow. This may involve the addition of natural isolates of bacteria or genetically engineered organisms, GEMs. There are rigid rules governing the release of GEMs as there is concern about their potential negative impacts on the environment. The genetic patterns have evolved over several decades and they are relatively stable. It is believed that altered genomes have greater stability and increase the chances of mutations, some of which may not be safe.
XC2 bioremediation is where the contaminated material is removed from the original site to another area for treatment. Methods of XC2 bioremediation include composting, controlled solid phase biotreatment, slurry phase bioremediation, anaerobic digestion processes, and bioabsorption of heavy metals. Composting is the biochemical degradation of organic materials to a sanitary, nuisance-free, humus-like material. It uses microbial aerobic decomposition processes to stabilize organic materials that may be used as soil conditioner. Controlled solid phase biotreatment involves processes that include treatment beds, biotreatment cells, soil piles, biopiles, or composting matrices where moisture, heat, nutrients, oxygen, and pH are controlled to enhance biodegradation. These processes are often enclosed to control expelled gases and include a leakage collection system and some aeration. This technique is among the expensive ones when applied. Slurry phase bioremediation is the treatment of excavated contaminated soils in the controlled environment of a bioreactor. Soil is separated into stones and rubble and then mixed with water. Electron acceptors and nutrients are added, and pH and temperature are controlled to optimize biological processes. Specialized organisms may be added if a suitable microbe population is not present. Both aerobic and anaerobic environments may be used. Anaerobic digestion is when organic matter is metabolized by anaerobic fermentation or anaerobic respiration in an environment free of oxygen or its precursors. This method has a long startup time and recovery time and requires specific nutrients, trace metals, and constant meticulous operational attention. Anaerobic digestion is more susceptible to changes in environmental conditions and gives off high sulfate wastewater that must be treated. Bioabsorption of heavy metals is the binding and concentration of adsorbents from aqueous solutions by certain types of inactive dead microbial biomass. This is done by utilizing the functional groups present in the biomass that have an affinity for heavy metal ions in order to form metal complexes or chelates. The advantages of this method include low cost, high efficiency, minimization of sludge, regeneration of biosorbents, and the possibility of metal recovery.
Although bioremediation is often seen as primarily a positive option to get rid of nuclear waste, there are a few negative side effects. For one, bioremediation occurs gradually and can take years to reach full completion. Also, in certain situations, the process can stall and more action will be required, requiring more time and money to be spent when the resources could have been spent doing things the traditional way. Stalling can also lead to an increase in the chances of carcinogenic substances being formed. Bioremediation can also release dissolved organic carbon, methane, hydrogen sulfide, and a variety of naturally occurring metals and metalloids, for example, iron, manganese, and arsenic.
The technology behind bioremediation is still relatively new, and people are still finding ways to utilize the technology. Like most technologies, developed countries are using it more than developing countries, and there is an ongoing urge for developing countries to begin implementing this technology. Industrial countries have strict regulations and regular monitoring from various agencies that limit the amount of pollution they are eligible to produce, but in countries that are becoming more and more developed, China and India, for example, there are less regulations and the pollution is becoming worse and worse. Many industrial countries are beginning to do more research to help developing countries implement bioremediation. Bioremediation research is being done at many different levels, from government research to research at various universities. For example, in 1996, the EPA began giving out funds for people that proposed new viable research for bioremediation. The project could not exceed 3 years or be over $500,000. There is also research currently being done by the United States Geological Survey and other government agencies. Private companies will also invest money in bioremediation research and develop products that they can then sell. One company that is in the lead of research in the U.S. is Regenesis Bioremediation Products Incorporated. So far in the world of politics, bioremediation has not yet become a hot topic of debate. In Europe, they have a yearly meeting called the European Bioremediation Conference, which serves to better implement bioremediation in the EU. While the EU is usually more restrictive on various topics, there aren't many restrictions on bioremediation, and there are several companies that have started in Europe that focus on bioremediation. In America, however, while there aren't restrictions on the research, there has been backlash against the government for investing in green energy companies when the economy is doing so poorly. But the Obama administration continues to make green energy and bioremediation a priority, including using bioremediation in the Restore the Great Lakes project.
Future research efforts will continue to isolate, mutate, and genetically engineer microbes to degrade recalcitrant pollutants, enhance degradation rates of target compounds, and ensure microbial survival. The modern biotechnological techniques being researched to improve bioremediation rates include genetic engineering, culturing of recombinant microorganisms, cells of animals and plants, metabolic engineering, hybridoma technology, nanobiotechnology, bioelectronics, protein engineering, transgenic animals and plants, tissue and organ engineering, immunological assays, genomics and proteomics, bioseparations, and bioreactor technologies. Genetic engineering efforts consist of improving strains and chemotactic ability, using mixed population biofilms, and optimizing physicochemical conditions. Gene expression in biofilm cells differ from platonic stage expression, and these differentially expressed genes regulate biofilm formation and development. Biofilms are especially suitable for the treatment of recalcitrant compounds because of their high microbial biomass and the ability to immobilize compounds.